Good morning, good afternoon, or good evening, depends on where you are. So welcome to today's Hong Kong Youth Science Distinguished Lecture. It's my great pleasure, probably first to welcome our Dean of Science, Professor Matthew Evans, to introduce today's distinguished speaker. So Matthew, you start.
Okay. Okay, thank you very much. So, dear teachers, students, and guests, welcome to the Faculty of Science Distinguished Lecture entitled New Operando Insights in the Catalytic Chemistry of Small Molecules. I'm Matthew Evans, I'm the Dean of Science. The selective activation of small molecules like carbon monoxide, carbon dioxide, methanol, and methane are of great interest as we're moving towards a more sustainable society. One that will be based less on fossil fuel and more on other things. The catalytic chemistry of these small molecules requires a profound insight into their reactivity. Hence, analytical methods have to be further developed, preferentially under realistic reaction conditions, the so-called Operando approach, to investigate the surface chemistry of related solid catalysts capable of converting these small molecules. In this talk, our speaker will discuss the latest developments in Operando spectroscopy and microscopy, thereby focusing on aspects of local temperature measurements, spatiotemporal assessment of reaction intermediates, as well as the long-term measurements with both lab-based and synchrotron-based X-ray methods. And it's my great pleasure to introduce today our speaker, Professor Bert Vechthuizen, who is a distinguished professor in catalysis, energy and sustainability at Utrecht University. For years, his group has been building powerful cameras to record what happens in the working catalytic solid. The long-term aim of this research is to bring this technology to a level that enables imaging catalysis at macro, meso and micro scales, from the reactor down to interactions between single atoms and molecules. He currently directs 2 national research programs, namely a gravitation research program on multi-scale catalytic energy conversions and the European initiative Synergy, which aims to foster the science and technology necessary to produce fossil-free fuels and chemicals to create a circular economy. Professor Vechthuizen is an elected member of various academies, such as the Royal Dutch Academy of Sciences and the Academie Europea, a fellow of the Royal Society of Chemistry, and many others besides. His research work is widely recognized and has received many distinguished awards, such as the Royal Dutch Chemical Society Gold Medal and the Burke Award from the Royal Society of Chemistry. And so without any further ado, I will now pass the floor to Professor Vechthuizen.
Thank you very much for the very kind introduction, and I hope I can now share my screen. And first of all, I have to thank you for being here, for inviting me, for making it possible just to go very fast to Hong Kong and back later today. This morning, I just joked to my wife, I'm going to Hong Kong. And she said, and are you tonight back? I said, I think so. So let's hope it's the case. And that we, in the meantime, also have been able to inspire you with a field which I think is very important. And I'm also looking forward to the discussion with the panel members. Some of them I really know very well. And I'm also wish to say is that I'm looking forward to visiting again and traveling again and coming hopefully to visit also you in the coming year or so, once we can again travel. My field is heterogeneous catalysis. These are heterogeneous catalysts, and in the introduction was already mentioned the multi-scale dimension, the multi-scale science. We have a large reactor, and this large reactor is filled with catalyst bodies, extrudates, you can see here on the left. When you further zoomed in these shaped catalyst particles, you can go up to what we call the active surface. The question is, how does that translate from the small nanoscale world, the world of atoms and molecules? How does it scale to macroscopic properties such as activity, selectivity, and stability? In order to answer this, and what our passion is to develop Operando spectroscopy and microscopy, and I will show you many of these examples today, how you do that. And what you do is you literally shine light on the catalyst under realistic conditions. You measure conversion, selectivity, yield as function of time. And what you want to do is to relate two information data boxes, sets, is conversion and spectroscopy or microscopy. And you want to link them. And then you have what we call structure activity relationships. And the overall aim is to develop new and better materials. We want to make an ultimate movie. We want to make snapshots. And we want to do that with a very powerful lens where we go from the reactor down, 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 down to single molecules and atoms. Why we want to do that? We want to make our society more sustainable, step by step. And what's important to realize is that this, what we want to realize is, what we want to realize is a more sustainable society step by step. And by doing this, that means that we will go from a scenario, which is, for example, here. Now we can build a future scenario, this or this, and that will require technological breakthroughs. And depending on the technological breakthroughs, we will be able to switch from fossil to more renewable resources, as you see here, from the current energy and materials mix to the future energy and materials mix. The refinery of the future. So the current refinery has mainly crude oil, and this is what we make out of it: gasoline, diesel, jet fuel, and others, plastics, and so on. But we believe that in 2015, the oil refineries and the refiners will look completely different. They will use captured CO2, they will use waste, they will use biomass. And of course, in alternative scenarios, maybe combinations with crude oil and natural gas, but certainly we will go into a mix. Also, the products we will make will be different, where more and more of the gasoline will be not anymore used because we will have an electrification of our car fleet, especially for short distance commuting. So it means that this is an overall scheme of a crude oil refinery, where crude oil is transformed in products, and you have several steps which maybe you do not need anymore. That means we will have to rethink, rebuild our refineries. And these refineries will be based on alternative carbon sources like CO capture from point sources or from the air, and they will be gradually then converted into small molecules. Actually, we will come into an era where we will have to deal with small molecules like methanol, CO, CO2, methane, and convert them into the products we make currently. And not anymore just cutting in pieces crude oil long hydrocarbon molecules. How could it look then like? And here I just put an imaginary scheme, a kind of visual of this. And what I put here is, this is the oil refinery, the new refinery of the future, using CO2 captured CO biomass waste. This is what all the windmills you need. This is all the solar panels you need. And this is, for example, the direct air capture you need. Well, it looks very impressive, because if you want to make, for example, a refinery which has only the half of the size of the current size of an oil refinery, then you have 5.6 kiloton per day long distance fuels you have to make, so many of chemicals, so many of plastics. And if you calculate it, and that is now something you have to believe. That means that you will have to have an enormous amount of windmills to build, an enormous area to cover with direct air capture solar panels. And also, if you count the 600 refineries we currently have, and we have to replace it, you need 7.5 trillion for green electrons only. This is a formidable challenge, which we all are confronted and what we have to do. My talk will focus on small molecules, which we want to paste. I want to talk about CO2, CO, and methanol, and for time reasons, I've skipped the methane. CO2. In this plot, I plot you the CO2 turnover as function of temperature for the thermocatalytic CO2 hydrogenation for base metals and noble metals. And here you can see in between the brackets the products you make. Methane, CO, methanol with copper, nickel mainly methane, and other metals give other products. The higher the temperature, the more CO2 you can convert. These kind of installations are already built, at least in pilot scale dimensions. For example, you can have captured CO2 from a biogas, biofermentation plant. That CO2 is then put into this reactor, which is filled with nickel catalyst for CO2 methanation. And what you obtain is an E-gas, methane, which you can directly inject in a natural gas grid. Now, what are the questions we want to answer? We want to answer what kind of metal nanoparticle of a metal, which can be nickel, copper, or whatever, is the best one to do this. And that means we have to introduce to you the concept of structure sensitivity, which means when the particle sizes changes, different facets are exposed to the outer surface. Hence, different sites are available, which can be sites on a facet, but also on an edge, or even you can have defects or fully coordinated metal atoms. We have been studying structure sensitivity by putting different nickel metal nanoparticles on a support, which for simplicity now is the most simple silica. And by doing this, we varied the nickel metal nanoparticle size between 1 and about 6 and even higher. When you do now CO2 to methane, and you can plot it as mole CO2 per methane per square meter per second, mole CO2 per methane per gram nickel per second, you see that you have a kind of maximum. And that means that at a certain particle size, you have the right facets and sites on the metal nanoparticle, which delivers you the highest activity. Why? So for this, we have been doing, and that is the first Operando method I want to introduce, is Operando infrared spectroscopy, which has this transmission cell. You have a mass flow and GC at the end. What you can do is to pass infrared through this cell under reaction conditions. You can measure for the different catalysts, and here I put catalyst A, F, and H, 1 nanometer, 2 nanometer, 6 nanometer. You don't have to be an infrared specialist to see that there are large differences between these different catalyst nanoparticles of catalyst. You can now analyze them in more detail. So I plot catalyst A, B, and C. And what I do is I just first start with the infrared spectrum of methane. So you make not so much for the small particle, not so much for the very large particle, and a large amount for the in-between particle size, which is in line with our GC and mass spec results. You can also measure formate. You make different amounts of formate depending on the particle size. You also make different amounts of CO depending on the particle size, both gas phase CO and adsorbed CO, and you make both linear and bridged CO. And that is depending as function of time and as function of temperature, which I don't discuss now, but also depending on the metal nanoparticle size. And that leads us to two pathways. A pathway starting from CO2 to methane going via the upper part or via the lower part, the carbidic part and the formate route. And we for both have an intermediate which we can identify spectroscopically. And theoretically, you can also assess that. Now, this is the organic molecules which are adsorbed on the surface. But what about the nickel, the metal nickel nanoparticle? For this, we have been doing at the synchrotron, at the Swiss light source quick X-ray absorption spectroscopy. What we did is we have been following the percentage of metal nanoparticle. And what you can do is you can do now switches in hydrogen, nitrogen, CO2, hydrogen, nitrogen, CO2, hydrogen, nitrogen, CO2, and the system will respond to this. What you do is you will, when you absorb CO2, you will lower the metal the metal percentage, as you can see here. When you reduce it with hydrogen, you will increase it again. By having that difference, you can actually calculate how many atoms, surface atoms respond. Actually, that's a very low amount, 3, 5. So what you see is that this behavior, you can titrate your active sites. We have been doing that as function of not only the particle size, but also temperature and pressure. And by doing this, you can vary the amount of methane, CO, and even make products like ethane, butane, and so on, carbon-carbon couplings products. When you have a minimum in couplings products, you have a maximum in C1 products. So we did not only do that for silica, but also for alumina, zirconia, ceria, titania. And depending on the support, you see that you can make more and more of this methane. Actually, the most methane you can make when you, for example, have titania around the support. So titania seemingly, or a reduced support, is seemingly a very elegant way to do something. And we have been trying to explain now why that is. And seemingly what you have is you have when you have the different supports, here you have alumina, sorry.
Sorry to interrupt you. The screen seemed to have been freezed. We are still seeing the second slides. Sorry, maybe just try again.
I hope you did not say that you did not see that you did you see my first. You're still seeing that.
Sorry, we see the second round, which is very good. We saw the preferential. Yeah.
Where did it stop then?
The second one. So if you try again, I think that if you try the second one, it should be okay, and then go afterwards. Yeah. Sorry about it. Yeah. Okay. It could be the
Which one you saw?
We haven't. If you have you done sharing, we can't see anything at the moment.
Oh.
If you yeah, if you try again.
You see my face?
We see. Yeah, we see that clearly. Yeah.
And now, do you see my screen?
Still not. The right.
Huh? It should be, no?
Let me see.
You see my face?
Yeah. Let me see.
There's an error then because from my side, I'm doing exactly what it should be. Wait,
is it because some?
So I'm going again. Screens, share screen.
Yeah. See again.
Then share.
Okay. Good.
Your screen is sharing.
Yeah.
Correct.
Correct now. Yeah.
Okay, now you have to tell me where you did not, where did I start that you did not see?
Now this actually.
Did you see this one? Did you see this one with this?
We see this one. Yeah, I think it's a 14, 15, maybe 19, 18.
Did you see this one?
Saw this one as well. Sorry. Yeah. It's further.
This one you saw?
So it's 21. I think it's 21. Yeah.
This one. Oops. This
yeah.
one you saw.
Yeah. We basically couldn't see the multi overlaps.
Okay, but
so
this one you no, but this one you have seen.
We didn't see this one. Sorry.
But this one you have seen.
Yeah, we just see here, but then I think you have multiple.
Yes. Okay, but maybe now you're in view of time. You have now to believe me. But what we do is we will wait. Huh?
Good. Okay. Thanks.
So this one you see. Yeah? This is one with reverse water gas shift reaction. You see that?
Okay, you can start from here. So start from this one. Yeah.
So this screen you see, yeah? On the left you see CO2, and on the right you see methane. Correct?
Yes. Yeah, that's right.
Okay. Good. Okay.
Thank you.
So, no worries. And you can interrupt me earlier if you do not see anything. Huh? So CO2. This is the carbide route. This is the formate route. And just double check. Do you see now this infrared spectrum on the right?
Yeah, it's coming. Yeah.
Okay.
I'll keep alive. If there's anything, I'll let you know. I'll let you.
Okay. So here you see the fingerprint for CO and formate. So this slide is a picture from the Swiss light source. I think there I was explaining. We did experiments where we have been titrating. I just double check. You see my screen where I have now Correct. 3 metal nanoparticles on the left. Huh?
Yeah.
Okay. So what we have is metal percentage. We measure the amount of nickel metal. So a high value is a lot of nickel metal. A low means that we have some of the nickel metal which is not oxidized but is interaction with an oxygen. Actually read or see it as that CO2 is adsorbed and oxygen from the CO2 is on the surface. So what you do is you titrate. What you can follow, you can calculate now how much it corresponds. Then you can count the number of atoms, and they are very, very small amount, a few atoms only. We did this not only as function of the particle size, we did also as function of temperature, pressure. What you see is that you have CO as function of particle size, pressure, and temperature, but also you can make C couplings, carbon-carbon couplings products like ethane. When you have a minimum of ethane, you have a maximum of methane. If you have a minimum of methane, you have a maximum of ethane propane. We did not only do that for silica, but also for titanium. And here I show on the right that the amount of methane is increasing when you go from silica to alumina, to zirconia, to ceria, to titania. Actually, reducible support seems to affect also the reaction mechanism. And what you see is when you go from alumina, silica towards titania, read more of this product you make, you see that you can have an alteration of the products you see. Actually, you have more of this formal route. So we thought, can we not take the nickel titania and try to see if you can use, for example, the outlet of a blast furnace exhaust steel industry CO2 point source. So the CO2, which is not pure CO2, but also contains some hydrogen and CO. If we do this, how does then now the infrared change? How can we now tweak the performance towards methane and C2? So for this, we have been making nickel on titania, and we have been playing with what is called the strong metal support interaction. Strong metal support interaction means that the titania is also reduced and will creep on the nickel metal nanoparticle. You can do this, and by having here, you can see, for example, methane 400 and 600 as product, and here you see 400, 600, 400, 600, 400, 600 with other products. What is the 400 and the 600? That is the 400 reduced, this is the 600 reduced. And what is the difference? More or less titania covering the nickel metal nanoparticle. Clearly, we can see an effect on the methane. And clearly, we also can see an effect on, for example, ethane or other carbon-carbon products. More carbon-carbon products when you have more of this titania creeping on the surface. We did exactly the same. We adsorbed CO and we did this analysis with CO bridged and also gas phase. And what is happening is you can also do XPS and measure the nickel. And what you then do is you can also measure not only the nickel, but also titania and estimate then the overlayer of titania on the nickel. And interestingly, you can see that when you have reduced CO and spent CO catalyst, that you see that some of the nickel is again exposed. So you go to very covered nickel with a CO reduced 600 degrees C, but once you have reaction, you see that it's again freeing up a bit of the nickel. So that leaves, this is the situation for the 400. This is the situation for the 600. The difference is the type of species you form. You see that you have a reservoir of formyl species in the case of this nickel titania, where you have a lot of patches of titania on the nickel. And we are now able to explain why you have here a faster reaction, a slower reaction, an enhanced carbon-carbon formation, and favored carbon deposition. I want to go further and do CO2 now, where we don't use hydrogen, but we use electrons to reduce. And we can do base metals and noble metals. And a very favorite element is copper. Now, copper can make different products. Can make, for example, ethylene. Can we see this? For this, we developed surface-enhanced Raman spectroscopy on a copper surface where we have roughened copper. This paper recently appeared in Ongoing Chemie. What we have been doing is we have been using CO2 in this surface roughened, and we have been measuring this species which you form on the catalyst. You can see again CO, linear and bridged. But interesting is that we also saw a low and high frequency CO. This has been possible by using and developing this Raman cell for Operando infrared in situ spectroscopy analysis, where you have this electrolyte and where you're able to measure also the Raman spectrum. We have been using a copper surface, pristine, reduced it, anodized it, and then reduced it. When you have this, you have enough surface roughness, not only to have reaction going on, but also to see Raman spectra. For example, here you're able to see for this anodized reduced, you can see this carbonate peak. This pristine is a lousy catalyst, not making a lot of ethylene. This one makes a lot of ethylene. So you see differences. Now we have been measuring different species as function of time. And very important is that we have been able to do that very fast in the millisecond regime. We can now, or the sub-second regime, we can measure bridged, low, and high frequency. We have been doing this as function of the potential versus the relative, the reference, minus 0.7, minus 0.8, minus 0.9. And what you see is you see that the ethylene is going up, the CO is going down, and you make also a little bit of methane. Interesting to us was that you see you have minus 0.8, it's rather stable, but the moment you make a lot of this ethylene, you see a lot of fluctuations taking place. The whole spectrum is changing when you go and increase the electron volt. And what you can do is you can now map the whole process from CO2, similar as I showed you before, not with infrared as in the case of the CO2 hydrogenation thermocatalytic, but now electrocatalytic, you can see even precursors for ethylene formation, which we identify as this intermediate with this frequency. So we're now able to measure both in the gas phase and in the liquid phase, thermocatalytic and electrocatalytic CO2 conversion. I want to go to CO. CO can be made from almost anything. Crude oil can be, of course, used right away, but coal, natural gas, biomass, and waste can be converted in synthesis gas from where you can do Fischer-Tropsch synthesis, a topic which is very familiar in Asia, and a lot of groups are active in this area in your country. We have been developing a sensor for Operando and a sensor for temperature. So we have been developing what is called shiners, which actually have been developed at Xiamen University, China. And we have also developing luminescence thermometry. And both approaches allows you now to measure vibrational spectra together as temperature. Here you see the Raman spectrometer, which we have the microscope and with the cells and the online lines for measuring, bringing the gases, but also for measuring the gases. And we have been developing this gold coated by silica, coated by rhodium with erbium, ytterbium co-doped yttrium matrix. This allows you to measure temperature by upconversion. The synthesizer, you can go up and then it falls back. And because of the Boltzmann relationship, you have two peaks with different intensities. These different intensities are 1 over temperature dependence when you do the logarithm, and then you get this calibration line. With this, you can now measure inline temperatures, and we have been doing that for many other reactions, methanol to olefins and so on. And we have a rather low error on this. Just to show argon hydrogen, so you increase the CO hydrogen, you see how the temperature can be followed by measuring the relative ratio of these two peaks. And you can see that you have now an internal temperature measurement in the catalyst itself. So you have a local temperature sensor, and now we want to have a local surface infrared or Raman spectrometer. For this, we used shell-isolated surface-enhanced Raman spectroscopy. The idea is gold coated with a titanium layer, you put ruthenium on it, and when you have this, you can now follow the spectroscopic signal. And it's important that because of doing this, you have a Raman enhancement. So the idea was, we have a silica extrude, we put rhodium particles on it, and we can now measure the temperature. This is the temperatures inline measured with this sensing device, and we measure at the same time Raman spectrum. And we can identify bridged, lineage, geminal, tilted, formyl species which we saw already before also with the CO2 hydrogenation, but now we see them also with CO hydrogenation. And you see different ratios. We have been able to identify them. For example, what is the origin of the 1780 centimeter band? Is it tilted CO or a formyl? What you can do is you can do hydrogen deuterium, and by doing that, CO hydrogen, CO deuterium, and so on, and you see there is no change. Hence, there's no formyl. So what you have been able is we have been able to identify, is it this route or this route? We have been able to see the CO dissociation, the product formation, the temperature, and we can exclude if it's now a formyl or a CO dissociation. We can even alter the relative bands, for example, bridge tilted linear, and we can see that when this is dropping, we make more of the oxygenates, for example, this ethanol or other products. So we found an internal marker for it. We wanted to go further, and one of the techniques which we have been developing over years is X-ray microscopy. And here I show you an X-ray microscope holder, which can maintain 14 bar. You can raise up to 1000 degrees C, and you can put here catalyst nanoparticles, catalyst particles. So you can put catalyst particles in between platinum heaters and shine X-rays through it when you have a synchrotron and measure then spectra. And that is what we developed. We developed it for measuring cobalt, carbon, and titania on a cobalt titania catalyst particle. We have an online mass spec, so it's truly Operando. And with this, we can now measure as function of time the carbon spectra, the cobalt spectra, the titanium spectra, and we can do it spatially resolved. And here I show you pictures of the catalyst as far at time 0.5, 17, 26, 47, 50, 65 hours. And then we have not only these images, but we also have spectra. And when you analyze them, you can identify different species, aromatic, aliphatic, oxygenated carbons, and they are spatially in this particle. So it means you have a particle which is a few micrometers in size, and across that particle you have gradients of carbon species in it. And as a function of time, you see that huge changes are taking place. Now you can identify that. I will not discuss them now in detail because X-rays are not so interesting for identifying. So we thought, can we not do that with another technique which you know much better, which is infrared? So can we bring infrared down to the nanoscale? So Fischer-Tropsch, you have different mechanisms which are proposed: the direct CO dissociation and the hydrogen assistant CO bond scission. So this is a mechanism where CO is dissociated, carbon and oxygen, and the hydrogen are then attached, and you see then a carbon chain which is growing. But if you have this hydrogen assistant CO bond scission, what you have is that you see here this formyl species, and also even you see species where you have an aromatic or a ring, where you see this kind of species where a carbon, oxygen, hydrogen is formed. Can you identify that? Can you see that? Can you distinguish that? So here at Utrecht, we have an atomic force microscope with an infrared nano beam. So you have a tip of an AFM and you shine infrared, and you can measure then infrared spectra. And you can see that you can measure a rather decent spectra. We made a model system, which is actually a cobalt titania shell, which you make on this silica wafer. And I show you that you indeed have this. And also we have about 4-5 nanometer in size of cobalt nanoparticles in this titania. So here you see this is the titania oxide, and then these small balls are cobalt. So that is what we did. We measured nano infrared. We measured also Raman, and we measured, as I showed you before, X-ray microscopy. So we have different nanoscale methods. And what you can do is you can follow as function of time the different species. Actually, what you can see is you see this growing chain. That's neat in my opinion. You can not only do that with CO16, but also CO18 and calculate even the number of what is happening. And here I show you theoretically, if this is a species which we would form, how would then the spectra look like? And here you see 18, 20, 70, 85. So we think we make this beast, this species. And we have reference samples, and we can even think about how long that chain is. So what we can do is we can now follow and measure, and actually we have evidence for this mechanism as well as for this mechanism. And what we propose is that for the flat terraces, you have this formation, and on the stepped cobalt surface, you make the hydrocarbons. And the formal route goes in this, and this one is the one which you have the linear paraffins, which you want to make. Methanol. Methanol is a very interesting molecule, which again, you can make from everything. You can make methanol from methane, methanol from biomass, methanol from waste, You can also make it from synthesis gas, and you can then follow it via the methanol to olefin or the methanol to gasoline route. What we did is we used an extradate, a porous catalyst, and we used a zeolite, ZSM5, and we used a binder, aluminum, in a 70-30 ratio. The whole thing is, can we understand what is happening in this extradate? We used the methanol to hydrocarbon. I come in a minute on it. And what you see is you make hydrocarbon pool species. But you see that spatially in that extradate, you have zoning. You have a rim and something deeper. And when you go further, you see that rim even is darkening further. So you have the top part and the bottom part. But actually what I did is we cut it just we have been doing that. So this is, you have to see that is just artificial. So it's just go the other way. But what happens is, if you would take now a fluorescent dye, seeming that also goes only to the top part. So what we say is we make hydrocarbon pool and deactivation product and aromatic rings, which are similar to these fluorescent molecules. Let's go for these fluorescent molecules, and we use these fluorescent molecules, and you can use different size fluorescent molecules. And what you have is, this is an extradate of 1, 2, and 3 millimeter. What you notice is that you have that you go more and more at the surface. So seemingly you have transport issues. Now, transport issues means you can quantify that as function of time and size. So here you see a stopwatch. You click, you see the smallest probe goes as function of time deeper and deeper in the material. So you go deeper and deeper into this particle. Now, similar things can happen with the methanol to olefin. So methanol comes at the outer surface, makes, for according to the hydrocarbon, these kind of aromatic things, and you go deeper and deeper and deeper, and you will have more and more difficulties to make this product. So you can somehow now start to observe these species. And for this, we need Operando UV-Vis. We made an Operando UV-Vis microscope, which allows us to measure spectra as function of different size, but also as function of different times. You make alkylated benzene, naphthalene, and so on and so on. And the spectra will shift in this direction, and you can see them spatially resolved in this extradate. And by doing this, we can see that the core and the edge is behaving different. Spatiotemporal changes, as was the case with, for example, the cobalt particle for Fischer-Tropsch, and we can now measure them. And we can do that as function of time, and we can see then the different species which forms in the core near the edge. We see transport boundaries, we see cracking happening again of these species. Hence, we can now correlate profiles of yields with profiles of species across these extradate. And it's a real example of multi-scale analysis, multi-scale science, where catalysts are taken really as a whole. So I want to end. I show you thermocatalytic, electrocatalytic CO2 conversion. I showed you pseudo-hydrogenation, where I showed you Raman spectroscopy via the shiners, AFM infrared to show you nanoscale infrared. I showed you nanoscale X-rays, gradients happening. I showed you at a higher scale with methanol, with UV-Vis and fluorescent methods. I showed you spatiotemporal effects of hydrocarbon species within an extradate. Only by understanding these spatiotemporal changes, by understanding them while they work, the Operando approach, we can make the new pasters of molecules, the molecules of CO, CO2, methanol, and for time reasons I've kicked out today methane, but are there, it's the same. Everything will shift towards more and more C1 chemistry. I think this age of this century will be also one where we will have to develop new tools, not only for carbon molecules, but even also, for example, for nitrogen to make ammonia and other molecules. Thank you for listening, but this has been impossible without all these people which you see here. It's a picture before the Corona time. It's a picture of not that recent, 2 years ago. Many thanks to them. It's their efforts which made that possible. I also want to thank all the funding agency, and of course, not the least, you for your kind attention, but also for hosting me here today online in Hong Kong.
Thank you very much, Professor Van Koosen. That is an excellent example of showing how little we know about small molecules and how complicated the reaction process can be if we look into the influences of processing conditions, temperature, pressure, and of course other compositions. And I think we have we may prolong a little bit given there's a large number of audience and big panels, but I hope that's okay. So we'll have another probably 20 to 30 minutes. Is that all right?
I have time until for my time 11:30. I have 45 minutes.
Oh, okay, good. Thanks for the generous offering. Okay, well, in that case, I'll open. So what we'll do is we will have invited questions from panel members. Panel members can, if you open your screen, we can see you. So if you raise your hand, we'll ask you to contribute to questions. For those in the audience, if you would like to ask questions, could you use the chat box? Then we can see your typed questions, and we'll try to, when we have time, we'll try to answer your inputs as well. Okay, good. So questions from panel first. Could I also note Professor CH3OH is also in the audience. Could I ask Professor CH3OH to join the panel as well, please? Yeah, thank you for your time to join us. Professor Xie is from Chinese University of Hong Kong. You can, if you open up your window. Yeah. Okay.
Yeah. Good. Thank you. Okay.
Okay. Good. So questions, please. Mm-hmm.
You don't have to be shy.
Don't be shy. Maybe I'll ask.
Wait, in the chat I see.
Yeah.
Okay.
You see many. Yeah. Maybe ask.
I see the chat. Yeah. Now. Yeah. Okay.
Yeah. Okay. Good. Yeah. So maybe yeah. No, I'll see. I'll give colleagues a bit of time to open up. My question is this, but it's actually it's related to the various observations. Now, clearly, you showed us the facets and ledges or edges.
Yes.
Can change selectivity. In other words, change not just the productivity, but also the selectivity. The types of species.
Yes.
And so clearly, that begs for question how do we control the nanostructures of the size, the facets, and the ledges? They are on the one hand interrelated. On the other hand, they do coexist.
Yes.
Yeah.
I will try to. So there are several paths people follow, and as well us.
Yeah.
Today I showed you. So the first what we did is we changed the nickel metal nanoparticle size, and by doing this, you change the relative size of the different facets.
Yeah.
That's first. We have theoretical calculations. For time reasons, I didn't show them, which shows indeed that depending on which facet and what is on the facet, you have different chemistry. Now, even for a particle which has the same size, let's say 3 nanometer, then you can start to play with the support. Support will creep on certain facets. By doing this, we change. Nickel titanium was an example. I just showed you today, actually we submitted to a referee, but then it came back. It was rejected. We are currently doing Operando in situ electron microscopy results to really show that the nickel, the titania creeps on this nickel, and that indeed then, if you would start to see the facets, which with high resolution TEM you can do, then you can start to say, okay, this is this facet, and then it's occupied or not with this titanium. There are a few things. First is, what is the perimeter doing around this particle? Is that storing, for example, CO, CO2 and things like that, molecules, atoms like that? Second thing is that we could also work with making bimetallics to alloy, to put other elements in it. Everything of this is under analysis, not only by our group, but also by other groups. So if we have full control over support metal interaction, full control over the size, and full control over the surface composition of the metals, then hopefully we have control over what sites there are. But you will always have that you cannot avoid, because of the practicality of a metal nanoparticle, that certain facets are then still there, maybe catalyzing a less selective route. So you're going for the catalyst with the metal nanoparticle composition, size, interaction with support, which provides you the highest stability and the highest yield selectivity.
Yeah.
I see a question.
Yeah, good. I see a question on
So I will read it. Yeah. Benedict Law. Hi, Professor. Okay. What are your comments in using diffraction scattering? Maybe synchrotron-based techniques for in situ C1 chemistry or in situ catalysis, given that the spatial resolution of the beam is increasingly currently down to about 0.5 in some beam lines. Yes, I think it's true. And I think what you will see is that that goes further. Now, we just published, and you can see a paper which we just published this week in JACS Gold. There's a new journal, JACS with gold, the open access. And there we published just a paper where we do ptychography, X-ray ptychography. And that allows us to go down below even 0.5 micrometer. So what you will see is you will see scattering, absorption, diffraction methodologies with synchrotron, which will be pushing more and more towards the nanometer scale. And if synchrotrons develop as they develop, then there will be the ambition at some point that there will be the 1 nanometer challenge and even below 1 nanometer up to the diffraction limit of X-rays. We are not yet there, but that is something you can expect and will certainly help to do that. But I would like to show you today, and that hopefully I mentioned that enough. I showed you today that we and others are not only looking to the inorganic part, the metal nanoparticle, the composition, the size, etc., but also on the organic part, what do we see at the particle? Because at the end of the day, it is the chemistry, the organic or the inorganic organic interaction. It's surface, actually it's organic, inorganic surface chemistry catalysis, nothing else. At least heterogeneous catalysis. And that means that that has to be understood well. And that is where we are trying to go.
Yeah, so particularly in developing the nanostructures, and Professor Zhang Hua has actually contributed greatly in, particularly on the phase of structures side. Maybe I invited Professor Zhang to maybe make some comments or questions, please.
Yeah, thank you, Professor Guo, and also thank you, Bert, for your nice talk. About this catalyst, I think now is quite a hot topic, especially for the CO2 reduction and so on, right? So you did a lot in this direction. Very nice work. I have a question about this phase-dependent probably study and also the catalytic application. Do you have any comment on it? So besides the size, morphology, architecture, dimensionality, and so on, do you think if you can get some unconventional or novel phase of a catalyst, how can this kind of parameter affect the performance of catalyst reaction? Do you have any comments?
What you want to say is that there is an uncommon, for example, an 2, 2, 3 facet or something like that, that you make a different metal facets. That's your question?
Not the facet, the crystal phase.
Oh, sorry, good. Yes. When you go to very small particles, what is at that moment a crystal phase? What I want to say with it is, at some point there will be, you know that in chemistry, people are also working with gas phase clusters.
No.
So you can go, or you come from, see, we go from the large scale and we want to control and make it smaller, smaller, smaller. And then we go from there and we want to see, and we make different things. And at some point we, okay, and then you make different facets and different, so on and so on. And on the other hand, you come from the bottom part where you have gas phase cluster and you say, okay, you have one nickel atom, you have a second one, or a cobalt, okay, and you start to have 10 cobalt atoms, and you add another 5. And then starts to be, what do we then understand under structure? And how dynamic is the structure? And how is the structure determined by the environment? It's like a catalyst at the end is a kind of chameleon. You change the environment, it changes its, yeah, I cannot literally show it, but I hope you understand. I mean, with my shoulder, you see, so you change the environment and the chameleon responds to it. And that means that I expect that crystal, I don't know if crystal phase is then the right wording, because it is, you have your surface, right, the surface, and then beneath comes something. You can have a crystal phase, but what is then this upper layer on it? And that means you will have to have very grazing incident methodologies. You will have to determine with energy, you go deeper, and then you determine here the structure of the phase and the surface. You have a lot of dynamics going on, and these things will certainly come up in the coming years. And I don't know if that, it's not really an answer, but somehow I'm trying to answer your question by giving it a
just like a polymorph.
Yeah.
We will.
Okay, because now
sorry, go ahead. Sorry.
I think limit, of course, just now you mentioned, right? The single atom, right? Single atoms. Well, now is quite hot. I think many people focus on this single atomic, catalyst, right? Of course, the air surface area is extremely large, right? When you get the atom and the second atom goes, and then after that, many atoms can form the cluster, right? If the cluster further grows up, of course, you get a nanoparticle.
Yeah, but I think okay, many people are doing at this moment single atom catalysis, but I would call it, I would like to have, for example, just 3, but then 5. And what is then happening? And if you can control that, just 5 atoms, and then I think that is something, that ultimate precision you want to have. For one reaction, you want to have 1, okay, a single atom, but you want to have 3, 8.
Sure, this cluster.
Or another number. Yeah.
Right. Yeah, I think also Professor Martin also focused on the single atomic catalyst. He did also a lot of work because after the single atoms, right? You can grow to the cluster and until the nanoparticle, right? So just now I mentioned, besides this kind of thermodynamic stable phase, crystal phase, or you can call crystal structure, you might also have some unconventional crystal structure, right? This somebody also called, especially physicists, also call this a metal stable phase.
Good. Well, I think it's a very good discussion. Yeah, clearly it could change the configuration surfaces as well. Maybe since Professor Martin is here, Professor Ma, could you can continue the comments and discussion or questions?
I think Bert is right, because in some of the cases, catalysis, I think most of the heterogeneous catalytic reaction cannot occur on a single atom, because I actually, for my paper, I don't like the term single atom, because definitely you have a support. It is it's your support that support your mental atoms, and this support definitely has some special role in the activation of your reactant or something. And more importantly, even for this isolated site catalysts, I would prefer to call it isolated mental site catalysts. It can only do a limited number of the heterogeneous catalytic reactions. For most of the heterogeneous catalytic reaction, it requires an example, a group of the mental, as Bert said, 5 or 3, a group of the mental atoms, which has already been actually discussed by our, it's a very old professor. No, he has already passed away several years ago. Wolfgang Zachtler, in 1980s or 1970s. That means most of the heterogeneous catalytic reaction needs example of the mental atoms. So I agree with Hua that recently single atom catalysis is very popular, but I do believe that most of the catalysts, most of the heterogeneous catalytic reaction need a group of the mental atom to finish its task. So this, I think, is most very important. So now the situation now the thing we need to do research or to working on is how many atom we need to finish a specific reaction, such as 3 atom or 5 atom, or the arrangement of the atom has some of the special effect on the activation of your reactants. That is what we want to working on. So in this term, the crystal phase sometimes will provide such as a specific distance between each atom that will benefit for the activation of your reactant. That is very important as well. But the priority of our task is to explore how many atom. Actually, previously when we're talking about size effect, normally it's begin from 1 or 2 nanometer. Then we're looking into such as 20 or 30 nanometer. But currently, because of development of the new synthetic methods, and especially the EM facilities, recently and also as Bert demonstrated today, the synchrotron facilities, they have all kinds of the using heterogeneous catalysis. We can look into the atomic resolution, how many atoms, such as 1, 2, 3, or 5, or you need 13 atoms. That is what we can do currently. But I have a question for Bert as well. So in European, I think several years ago, you already began to talking about carbon neutral things. Last year in China, carbon neutral become very, very popular because the president has speak it out. Besides CO2 conversion, what do you think our heterogeneous catalyst people can do for this carbon neutral version? What we can do besides CO2 conversion? I think CO2 conversion is a big project. But besides that, under carbon neutral version, what we can do for our heterogeneous catalyst people? Okay.
Well, there are a few things. First, I think is we should. What I did not discuss today, I think we should go for circularity.
Yeah.
Circularity of elements. And circularity of elements is carbon, CO2, but also holds that all our products we make should be designed for circularity. That means we have to rethink plastics, we have to rethink coatings, we have to rethink several things which are made to be taken apart again, where from your base molecules you make again that material. So I expect that multi-layered plastics and coatings will have to be designed and made catalytically in such a way that you can easily remake them from the waste.
Okay.
Waste is your carbon source. There will be, at the end, there will be no waste. It is like when, at least here in Europe, and I'm sure in China, if you would ask a farmer if he has waste, the farmer will always say, we have no waste. I use everything.
Yes. Yeah.
I think we should rethink that we, in a city, we don't have waste. No, everything is a carbon and a nitrogen, a phosphorus, and sulfur. So as chemists, as catalytic scientists, I think it's the era, this century is the era of circular chemistry and catalysis to make that happen.
Yeah, I
that
agree.
means we have to rethink our process of materials making. Yes, we have to make catalysts to upcycle and recycle plastics and biomass waste and agricultural waste and all that stuff. Yes, but I think we should also start to rethink how we make our materials. And that is something that is only going, I think, slowly, because we are used to all these materials, and we do not want to give in on the luxury. I mean, my son, my daughter, they just want to have still their iPad and their iPhone or their whatever, or they want to have their toy or all these things. And us, we want to have a car and we want to have it smooth and we have to have decoration in our house. So that we will not easily give in. But what we want to do is to make, I don't think that the consumer would mind if it is made in a different way, but it's still having functionalities as it is he or she is used to. And that mental thing, that is, I think, what we should do. We should see chemistry as the solution, catalysis as the solution. We will make our society more circular. I hope so.
I agree with you.
Okay, that's a great, I think it's a great comment from, particularly from scientists wishing to be much more responsible for the future of our society. Now, on that note, can I invite Professor Xie to make some questions and comments as Professor Xie has been working on similar topics. Yeah, please. Yeah.
Thank you, Professor Guo. Yeah, and let's also thank Bert for exciting talk. See, I'm not working in heterogeneous catalysis. I'm working in homogeneous catalysis. So my question is, since you have pointed out that, for example, for the catalyst size will affect the selectivity and reactivity. So my question is, maybe I missed something, the size effect, selectivity, and the reactivity. Could we understand the relationship very well, or you understand it, or you want to make a comment? How do we understand the relationship among the size, selectivity, as well as reactivity?
Yeah, okay, I don't want to use that too often as argument, but we published a year ago in Nature Communication a paper where we did theoretical calculations on nickel metal nanoparticles as a follow-up paper in the make. And there we really calculate microkinetic wise what nickel facet site gives what product with what rate, and which somehow, I'm not saying fully agree, it agrees, but is in line with experiments. What the difference is between homogeneous and heterogeneous catalysis, in my opinion, is that the control over the uniqueness of the site is better defined with a homogeneous catalyst, because your ligand or your ligands will coordinate around a certain transition metal ion or metal, therefore will give that state. Now, there's one thing that is, in your case, that is what you have X-ray diffraction wise determined, but at the moment you put it in a solution or in a reactive media, also that system will respond. That will also not be unique. It's unique when you start. You start with a more unique system as a heterogeneous catalyst. We are jealous to the precision you can make. But what we offer is a thing that we have the temperature and the pressure not, but the temperature span we can cover is something different from a normal homogeneous catalyst. You say, can you now tailor it? I think we can now more and more, or better and better, tailor the active site, especially when we use, for example, a host like a zeolite or a well-defined host where we put the metal ion in, because then the zeolite or the inorganic host starts to be acting like it was this ligand, organic ligand you have in homogeneous catalysis. But it's fair that we cannot beat the selectivity of for example, an enzyme, where even there, other effects like allosteric effect and whatever, other aspects of complexity are built into the system. Now, I'm expecting that a catalyst will become more and more a device, that there will be a time where we will be able to really by precision put there, and there a certain metal nanoparticle or metal whatever active sites there with a certain composition size, and separate it from another one and from another one, where you can do almost like you do in a membrane and like in biocatalysis, where you could do cascade type of reactions. That I think will become reality. Not now, but I think for all the young students here in the audience, it's your time. You will make it.
Great. You mentioned another very fundamental central challenge. Yeah, thanks for that. That's a great, great question. Particularly, bridging the homogeneous and heterogeneous entities in catalysis. So we have another external panel member, Professor Junwang Tang from University College London. Junwang, are you still there? I'm sorry, I was. It's good. Can I invite you to contribute in questions or comments? Thank you.
Thank you. But can you hear me?
Yes, good.
Thanks, Professor Guo. Thanks for organizing a wonderful talk. I think you both give lots of information. I do need the time to digest your information all the way from X-ray absorption and Raman infrared. In fact, I have one burning question, but you just mentioned that you can give us more chance to discuss with you because you have 45 minutes now. I think maybe 20 minutes left. I can probably ask you a few more questions. One thing is, I think the question linked to the question asked by Professor Zhang Hua and Ding Ma. When your active sets move down from a few nanometer to sub-nanometer, and you also use the X-ray absorption to observe what happened on the surface. Now, my question linked to that one: if we use a strong X-ray or synchrotron beam, the energy is so big. I don't know if this sub-nanoparticle is stable, or what we observed on the surface is true, or is something which not happened in the real reaction because the thermocatalytic reaction all take place at a few hundred degrees C. That energy much smaller than X-ray beam. I think the particle says no, it's 1 or 2 nanometers, or maybe smaller than 1 nanometer. It's not that stable. It's a strong X beam change the particle completely, and then move from maybe amorphous to a crystalline or crystalline to amorphous.
Good, very good question. But you see that more and more we are, not more and more, we did it already in the past, but you see that we showed infrared data, Raman data. These kind of techniques will be less damaging or less perturbing. But I have to say, even that is not even true, because if you have a focused infrared beam laser, and if you have a focused Raman or visible laser for Raman, also there you see effects. And now you also understand, although I did not explain that maybe too well, why would we like to have this temperature sensor locally? Because we want to measure locally what the effect is of the temperature, not only the temperature, what the reaction is, but also, for example, beam on, beam off, X-ray on or X-ray off. Years ago, and it's maybe good for the students who are in the audience, if you look up in my CV, you will find 2 papers in Journal of Physical Chemistry, B or C, I forgot. And these 2 is about, and I make the link to homogeneous catalysis. We used homogeneous copper complexes for doing a reaction. And we used X-rays to follow that, time-resolved X-rays. What was the effect? The effect was that the X-rays actually were damaging the solution. It was an aqueous phase reaction. Actually, what you had was you had radiolysis. You made hydrogen, or radicals. You made hydrogen, and actually the copper was not anymore a complex, an isolated copper, but copper became copper colloidal species. So that was an example, or is an example, where X-rays really literally, you can see it by the color change, that copper 2+ went to copper 1, and then even copper metal, and colloidal particles could be identified after the use in a synchrotron. And we had experiments beam on, beam off, beam on, beam off, and you could see the effect. We also have published a paper also years ago where we had a laser. We had a local infrared camera, and we measured the temperature, laser on, laser off, temperature up, down, up, down. So, and most recently, we did it for this electron microscopy, Operando in situ cells, which are commercially available, which people sell. What do we notice? That the temperature in that cell is not the temperature you believe, because you have a gas flowing over it. So it means you have a heat capacity of the gas. You have the X-ray, which is hitting the sample, and all that contributes to changes in temperature and the catalyst and so on. Measuring is perturbing, unfortunately. You would like to have a measurement which is non-perturbing, but that does not exist. You have to minimize the effects. And now I come back to then your more challenging. If you then go further and further and smaller and smaller and smaller and smaller and smaller, and you have to put then, because you have less and less material, you have to have more and more energy to get something out of it, then I think there will be a moment that indeed your uncertainty, to say it, although it's not correct, formally correct, but think about Heisenberg uncertainty principle. So you're doing more and more effort to reach something, and you're getting more and more away from your real answer because you will not reach it. So there will be a moment where, despite all your efforts, your uncertainty on the result will be getting huge, and you will not learn anything anymore about catalysis. You will learn about something else, which is not catalysis anymore. It's not an answer, but I think it's more philosophical. But therefore, I feel we should develop also the lower energy tools. The lower energy is infrared, but even an infrared laser is still not innocent.
Thanks, but that's my concern, because I would worry about is that all these top journal paper use this very strong synchron beam to observe what happens. It's worry about that gives some, as just an uncertainty, which is misleading the whole society to move the other direction. And the quick question is about your infrared. You give a wonderful example about the spatial resolution.
Yeah.
Can you let us know what's the time resolution for this infrared beam?
Oh, the infrared. That is not too bad. It depends. No, the whole point in imaging is how many pixels do you want, space resolution wise, and the more pixels you want, the more you have to scan or to. And then you have time. So space and time at this moment are orthogonal. Just if you want to get high space resolution, you give them time, and the other way around. But once you have measured the space and you know what it is, and you sit down on a point, then I think it goes rather fast. And then I think with infrared Raman, I showed you this source for CO2 electroreduction, and we are pushing it now below the second. Milliseconds. People are also going. You want to go. So sometimes people then argue how far you want to go. Of course, ideally you would like to do like Ahmed Zewail, the late Nobel laureate, where you want to go really making films. But for catalysis, the elementary steps are, or the rate determining steps are often in the millisecond regime. And so I think if we are able to see diffusion, reaction, or the rate determining step reaction, and we could visualize that already, I would say is that I'm not saying that I'm then happy, but I'm not unhappy.
Good, thank you. Just a quick comments from me. No
oh, sorry, and really the question, wait. And I'm saying because you can measure currently an X-ray spectrum in a tomographic sense in seconds, minutes, and so on. So, yeah. But if you want to really have an image 3D, well, then you still need minutes, hour, and then you see that you have snapshot every X hours. Sorry, good.
Yes.
Back to you.
Thank you. So what my last comments is about Dingma mentioned there are some wonderful results, fundamental understanding report 20, 30 years ago. One of my suggestion is maybe this fundamental understanding report of 20 or 30 years ago are good, or maybe not very accurate, because technology used by them is not as accurate as advanced currently. So for fundamental understanding, we should trust the new results, the recent one, rather than the old one. Experiment results, we should choose always that, observe that.
I've one thing I want to say about this. We are there will be soon. I mean, it's almost accepted. There's a new journal, Catalysis. It's from the Chem group. Chem Joule as a new catalysis journal. Catalysis? I forgot. Yeah, something. And Catalysis, we wrote a review paper on Fischer-Tropsch. And the PhD student, Iris ten Have, was looking into the literature. And what I find so interesting is that often hypotheses come and go. Many of the things which we discussed were 100 years ago or 50 years ago, they were also there. The question about, is it a carbide mechanism? Is it a formate mechanism? If there is, for example, cobalt Fischer-Tropsch catalysis or iron Fischer-Tropsch. Is it a carbide, an oxide, a metal, all these things? Everything of these bigger questions, they are out already for years. With all the new methodologies, theoretically, experimentally, we always have to reassess these questions and try to see if the answer which we had is the correct one. because if you have a new tool, you will see with a certain where are my glasses? Just okay. So you're having a certain view on something. But what I also mean is maybe you do this, and the next technique is doing this.
Mm-hmm.
So you need to have many glasses, many views. So it also means we will have to be the crux will be the synthesis of all the results, bringing all the data together. That's not easy.
Yeah. Maybe that on that note, maybe the current emphasis on machine learning could probably play a role in this. Particularly, have a lot of information in this. And then maybe could I invite my thanks, Joanna. That's great. Yeah, invite my colleague Hongja. Hongja's actually again can inject views from a different angle. Hongja's working very extensively on this biocatalysis and bio systems. Of course, in organic in many ways as well. Please, Hongja.
Yes, in fact, I'm a layman on this catalysis, and especially at nanoscale clusters. And so there are, of course, the advantages and disadvantages. And so in this kind of a catalyst, then I'm just wondering whether what we can learn from nature, and then how can we make those catalysts better than, for example, those in enzyme. Because in native, you see, we hardly use these clusters or nanoscale catalysts to catalyze a variety of reactions. And so I don't know whether, Bert, you have any comments. And for example, when we design this catalyst at this nanoscales, we may have any additional advantages comparing with those in the life process.
Well, the first is that we have to realize that catalysis in enzymes, although it's not completely true because there are enzymes near volcanoes and also in the deep sea, also species which are doing at high pressure and high temperature things which we as heterogeneous catalysts have only to admire. So we have to be modest, be synthetic people. But there's a difference in that the nature has a way of repairing things and an internal recycling system. When I discussed with Dingma the whole thing about circularity, we also have to think about circularity in catalysis. Circularity in the active site in your body. I mean, in my body, I mean, I had my coffee and whatever. So here in my stomach, all the enzymes, but they have a certain lifetime. They have a certain turnover number, and after that, the game is over. And if it's is not, then I'm getting sick because there is another disease happening. But that whole thing about switching off your activity, going latent, then being destroyed and making from the same elements again a certain enzyme, I think that is something what we have to learn from nature, that we should think in. I mean, when I talked about the farmer does not waste anything, let's be also clear, our body also does not want to waste a lot. We'll also try to maximize things. This adaptability, that cooperativity and so these kind of concepts we will have to start to embrace more. In the US, there is I think it's Cornell University, Peng Chen, Chinese researcher. He is a professor. He, for example, is coming from Ed Solomon from Stanford University. He's trying to introduce now this kind of concepts of cooperativity and things like that into the world of heterogeneous catalysis. But I think we are, When I was a student, PhD student, we talked about zeozymes, zeolytic enzymes, where we wanted to use zeolites as hosts for putting active entities to mimic enzymes. For that, from there, the name zeozymes. But still, the work is still very rudimentary compared to enzymes. We should be modest scientists in that respect.
Good.
It's not an answer. I think it's more a philosophical comment to you.
That's good. Yeah, we still, it means, yes, we still have a lot to learn from nature, definitely. Jin Yao, maybe I'll ask another colleague, Jin Yao, to come now.
Oh, hi.
Okay, yeah, well, I'll come back. Yeah. Okay, sorry.
Hi, this is Jin Yao from chemistry department. Like, I'm not really doing too much catalyst, but like, I think this is a general works. Like, I think it's for other students. Like, they also ask this. I try to rephrase my questions for this because I have thinking about this for quite a long time. Because when you're actually doing a catalyst, actually I have two questions. The first one is when you have a reaction, so we know that the catalyst is actually also changing as well. So the surface is actually changing constantly. So like in this case, like your new technologies or new techniques can actually see those changes, like, because I think this is going to be related with the catalyst degrade or catalyst going to be have a long time stabilities, because I think industry is also like really like that, right? This kind of question.
They really like it. I can tell you that we are working together with industry and we are trying to implement some of these methods in a more industrial environment. Second is that the methods which I described are not limited to catalysis. You can use them for batteries, fuel cells, materials research in general. And also there, the Operando ID is there because Operando means just while something is operating in a fuel cell and a battery, operating means something else than in a catalyst. That's all. Sorry.
Yeah. Okay. So that's fine. Like this, like another question is like, I think it's right now we have reactions is actually happening in the gas phase, like heterogeneous catalyst, and also one is in the liquid phase. So what do you think is the main difference between these two? Because I'm working in the liquid phase always.
Yes,
it's going to be completely different, like in many sense, right?
I showed you today gas phase catalysis with the exception of the electrocatalysis, but I can also there's a paper which is almost now submitted, which we do infrared type experiments on lignin conversion. People who follow our work, they know that we work on lignin conversion, the liquid phase. And liquid phase spectroscopy requires completely different ways of analysis, because the problem is you have the solvent. The solvent is dominating. So you have dominating phases. So the gas phase, you have your reactant. The gas phase mean let's say it's in that way, the partial pressure is completely of the number of molecules you have is completely different from the gas phase compared to the liquid phase. So the solvent, the liquid, will be dominant in spectroscopic data you measure. And another thing what we already discussed briefly is the beam damage you have with a liquid. A liquid can then much more interfere. So there are several, but I mean, we have been developing in situ Operando cells for both liquid phase and gas phase catalysis. I think I would not say it's more difficult or more simple. I would say it's different challenges. Yeah.
Okay, yeah. Well, like I think it's in terms of chemistry point of view, it's like in the liquid, it's going to have a more solvent, so those solvent molecules going to have a diffusion limited for the mobility of your gas, your species. So you're basically getting a completely different set of environment. It looks like to me. Or
okay, if I may advertise a paper, we published a paper in JAX a few years ago with single molecule fluorescence, and we show actually the effect of a solvent. We show that in the case of solvent is around and hydrocarbon solvent, the hydrocarbon is actually blocking the molecule to react, so you will have less reactivity, you change it with another solvent, and you see that there is, so you have competition between solvent and molecule, for example, solvent and reactant. But that is something you also have in the gas phase. Also there you have competing reactants in the gas phase who compete for the active site.
Mm-hmm. Okay.
But with a solvent, so many of them.
Yeah.
Then you have more.
But in this case, like, okay, so my final question would be like, because I know like some people are doing there's a methane, so methanols, the kind of reactions, CO2 reactions. So some is doing in the gas phase, some is doing in the liquid phase. And we got comments like says, okay, basically like you're doing science, that's fine. But if you're doing the industries, like the liquid phase is not really the way to go because you don't have enough throughput and you have a lot of problems with the liquid phase.
Yeah, but you have, for example, that is true. You have issues with. But I would not. I do not. To my students, I always, and I tell us if the students are here, then I just tell, I do not like when my students come and they say we have problems. I always say you have challenges, not problems.
Yeah.
Problems sounds too negative.
Okay.
Challenges you can overcome. Challenges you can solve.
Right. Yeah. But do you think it's a feasible way, because like people are doing the liquid phase, like methane oxidations, methane to methanol conversions, those kind of.
Optimistic. I'm an optimistic man.
Okay. That's fine. Yeah.
I mean, I think if I may be fair on that, I think we too often, of course, experiments are very difficult and all that, and so I don't want to underestimate it. But we also have to be open for the challenge. If you right away, sometimes what I also tell to some of the students is, if you're right away already in your mind already say this is not possible, that is not possible, that is not possible, and that is the reason why it's something not possible, then you will never do the experiment. While it's sometimes good just to do the experiment.
Yeah.
And then you will see what the real problems are.
Because sometimes like I think it's if the student know like, okay, why this is not possible, so he already know like the problem, so like this is probably the starting point to actually solve the problems, right?
Yeah, that's true. But on the other hand, sometimes what I call, you can overanalyze the problem.
Okay.
Sometimes the challenge is just to do it within reasonable. I have to end my talk.
Indeed.
I hope you allow me, because we are already 8 minutes over the.
Sorry, Edmund, I was just going to, in the course of time, maybe we'll stop here. And again, it's great, a great talk, and even great discussions and contributions from various members of the panel and from the audience as well. So we hope to have more opportunities to invite Professor Mahosin to Hong Kong, to China, and we'll have more opportunity to interact.
I really hope to come. So be sure that I really want to come.
Definitely.
I want to come also to my other colleagues. I'm looking forward, Dingma, to our favorite restaurant in Peking, of Beijing.
Okay.
And many thanks for having me. I hope also the students that you have learned, you can always email me in case you have still some questions. And I wish you a very nice day, and many thanks for having me here. It was an honor and a pleasure to do this.
Thank you again, and thank you, panel members and audience, and of course my colleagues from the admin, particularly later hours of the day, are still faithfully supporting us. So thanks again. See you next time. Bye bye.